Greetings to all attendees. COSASCO is glad to have you here today in this webinar that is part of the training strategy and commitment to transferring knowledge to all our clients and allies, always providing the best support and technical advice based on the latest industry standards to improve the reliability and operational safety of your assets. This is the fourth webinar as an incredible added value for you being part and user of our COSASCO technology. With more than 70 years of experience and technological development worldwide, we provide the best products for corrosion monitoring in all environments. The rules for this webinar are simple. All questions need to be placed on the chat box. If you didn't register previously, please leave all your contact information, including country, company, name, and email, on the chat box. At the end of this webinar, we will be answering all the questions or most of the questions you made in the chat, and next week we will be sending a link for you to access to our webinar training material. As this webinar will be recorded, we ask you to turn off your cameras. The only camera that will be on will be from an expert. We're also going to provide a survey that we truly appreciate you to respond, as this will allow us to continue and improve this kind of activities. Imagine and picture all the tools that you will hear during this presentation that will allow you to interpret and articulate the best monitoring strategy by moving through the different technologies and recommended practices, transforming and improving our selection criteria for internal corrosion monitoring systems, evaluations, and diagnostics in pipelines as part of the Asset Integrity Management Program. Today, we would like to thank CIMA-TQ LLC for being our partner in this specific activity. And I want to introduce you our NACE senior expert for today's sessions, who has over 35 years of experience in several areas related to corrosion and integrity management. We're very lucky to have one of the most important members of the internal corrosion community, especially NACE, as an active NACE instructor for basic, advanced, and direct assessment training certifications. Many times awarded for his contributions to corrosion science, and he is also a scholarship promoter for all community related to corrosion. Please welcome from CIMA-TQ to the Master, PhD, and NACE Fellow, Carlos Palacios.
Okay, I think I'm unmuted now. I think I'm okay now. I hope everybody can hear me. So now I'm going to start sharing the presentation. Usually with these video things, nothing goes as planned. So hopefully everybody is listening to me. If not, please write it down in the chat and David will let me know. So as David mentioned, welcome to this seminar. In this seminar, of course, is focused towards internal corrosion, and I'm gonna give a little bit of an introduction on different aspects of pipeline integrity. And then I'm going to focus on the different monitoring and why the importance of monitoring to assess the integrity of pipeline systems. As David mentioned, please, if you have any questions, just write it down in the chat. Even though at the end of the presentation, I'm going to stick around for a little longer to answer most of the questions that you have. So there is no pressure for time from my side. It's only from your side. If you need to leave, well, that's fine. So my name is Carlos Palacios. As David mentioned, I've been 35 years of experience in the oil industry, exposed to many different conditions in the fields and especially to monitoring. My company is CIMATQ. I'm the president of CIMATQ. That is a corrosion and integrity management and treatment quality company. So starting with the presentation, you may ask yourself, what is that surfer doing in that slide right there? Well, it turns out that nowadays, many of us, many companies are basically riding the wave of integrity management. So this is something that is been going on for a few years now. And those companies and those of us that don't get riding the wave, we're going to be left behind, or we may be turned over by the wave. So because integrity management is becoming more and more of an issue in every company, not only in the oil industry, by the way, it's basically throughout many industries, because the importance of integrity management is maintaining the fluid inside to avoid issues with the environment, safety, etc., etc. Now, when we think about the number of pipelines or the length of pipelines that we have in the world, it is amazing to see how many pipelines do we have. And by the way, pipelines are one of the most, or I would say the safest way to transport hydrocarbons. We do have some issues where integrity management is not performed appropriately. But even though those issues that we had or those incidents that we have had, still is the safest way to transport hydrocarbons. So when we look at that table, I don't mean you to add all those numbers. I add them all for you. This is the Earth, and the circumference of the Earth is 24,000 miles, 39,000 kilometers. And we have in the world about 100 times that length around the Earth. Think about this one. I mean, 111 times the length of pipeline to go around the Earth. It's a huge amount of pipelines. And we have to care for these pipelines. We have to maintain these pipelines. So how do we do that? And the other thing that is important to mention here is that many of these pipelines may not necessarily be piggable. Piggable means that you are able to launch some cleaning tools or inspection tools to assess the integrity of the pipeline. And then how do we do with those pipelines? It is estimated that in the United States alone, about 65% of the pipelines are non-piggable. Nowadays, we cannot even imagine designing a pipeline without it being piggable. I mean, it is a must, but it's amazing. But one thing, but I would say with a word of caution, because if you go to the upstream business of the oil industry, meaning from the well to the flow stations, for example, not necessarily all those lines are piggable. And that's also important than the monitoring of our installations. Now, when we look at some of these integrity threats, okay, we have what's called the time-dependent threats, such as corrosion, whether it's internal or external, erosion, and in many cases, that's where most of the monitoring, at least the monitoring that we're going to be talking about today, is what it's being used. okay? We have also some threats for third-party damage, such as third-party damage. Third-party damage, somebody else comes with a hammer, hammers the pipeline, a backhoe digs a pipeline and hits the pipeline, or somebody malignous come in and basically saws the pipeline and opens a hole. We have bad operation. I mean, doesn't mean, I mean, if the operator doesn't have the necessary training, may operate a separator, for example, badly, and then issues of water into the oil or water into the gas stream become an issue downstream. Of course, engineering. This is important because when we are doing engineering in pipelines, we have the power of the pencil. And when we are doing engineering, that's where most of the mitigation or our battle against corrosion, we can win while doing in engineering. The question is, do we have the experience? Does that specific engineer that is designing your pipeline have the experience in the area of corrosion? Do we know how or where to put our monitoring devices? I mean, we always have to think about these things, because one thing is what we do in an ivory tower, such as the energy corridor in Houston, for example, or maybe in a beautiful building in Madrid designing a pipeline. Now, do we know where is this pipeline going? Do we know the environment of this place where the installation is going to go? So we have to be in contact with the operator, and also, of course, with the corrosion engineer, so that we design the pipeline friendly to minimize corrosion issues. Another threat, natural forces. How do we prevent natural forces? Sometimes it is impossible. We may not, it may not be practical to be designing a pipeline thinking that I'm going to have an earthquake in 15, 20 years, because the probabilities of an earthquake may be low. Or depending where you are, like if you are in California, the probabilities of an earthquake is high, but then we have to be looking at the consequence. Then we are entering into a concept of risk management. Now, how do we prevent natural forces? I have some examples that I'm going to share with you. The first one here is the third-party damage. As you can see, right next to the well, there is a hacksaw. I mean, that's not corrosion. No way that is corrosion. That has been done on purpose. Of course, many of our systems, or many of the systems around the world and in other countries, you know, when something like this happens, means work for the locals, because now we have a failure, we have a leak, we have an environmental issue, and then the locals may get involved into fixing the environment. So these are things that, I mean, how can we prevent that? Of course, as I said, there are ways of preventing. We could put a fence around it, we can put cameras, etc., etc. That is a different type of monitoring than the one that we're going to be talking about today. Now, geotechnical effects, natural forces. How do I combat natural forces? Here on your left, you have a huge mudslide and a rock. Here we have a train tracks. We may have had a pipeline. How do we prevent that? Then we need to know about the geotechnical aspects to put the proper fences in front of the pipeline to prevent something like this from happening. Here on your right, what you see here on your right, this is a wellhead. This is a well. This is a wellhead right there on the top. There used to be a soccer rod pump right here on the top. All what you see here is the cement around the casing of that well. This happened in 1999. There was a huge mudslide in the north of Peru in the Talara field. And this mudslide uncovered many of the wells, and this is one of those wells. So how do you prevent that? It becomes very difficult and it becomes unpractical. Therefore, you're going to have to live with that risk and manage the risk after the fact. External corrosion. Now we are back to one of the time-dependent failures. External corrosion, yes, it can be monitored. There are different systems that we can use to monitor external corrosion, to monitor the corrosiveness of the soil, and then prevent it. Of course, nowadays, there is no pipeline that goes underground without a coating. But remember that coating is only one barrier. In addition to the coating, we use cathodic protection because we know that there is no such thing as a perfect coating. And therefore, we use cathodic protection as the second barrier. So we have a coating and we have cathodic protection. But once again, if somebody may come in with a backhoe and do some damage to the coating, or maybe the movements of the pipe inside the soil may damage the coating, and then we may have a failure. And there are ways of monitoring those. Finally, we are going to enter into the internal corrosion part. What you see here, this is a pipeline, okay? Actually, this is a multi-phase flow pipeline. In my experience, one of the most difficult things to prevent or to mitigate is corrosion in multi-phase flow systems. Multi-phase flow systems, they carry gas, oil, water, sand, and anything else your little heart desires. And therefore becomes a very nice challenge to mitigate corrosion and in this type of pipeline. And in this specific example, we're talking about in an upstream system in which may not have been piggable, and therefore I'm not going to be able to maintain the life of the pipeline because it's unpiggable. Yes, we did have some monitoring, not properly located, but we had a lot of issues with corrosion. Now, this is not monitoring related, but I'd like to ask you, and please answer in the chat, and I will answer that question after a little while. Can you tell the flow direction on this pipeline? And if you can you also, when you look at something like that, can you see what else is happening inside that pipeline? Where is the water? Okay. So I imagine that most of you have answered already if which direction is the flow. And I'm going to answer, when we have flow assisted corrosion, there is one distinctive morphology on the pipeline that can lead us to believe what is the flow direction. And I want you to pay attention on how I am stating what I just said. Because when you look at the morphology of pipelines, it's very difficult by just looking at the dead body, which is the pipeline, is right there, and they give it to the corrosion engineer and they tell them, okay, tell me why this thing failed. Looking at the morphology of a pipeline is very difficult to tell what was the cause. There are perhaps 5 distinctive characteristics that can lead you to believe one way or the other, okay? That's a subject for a separate seminar, but I just want you to bear in mind and take with the message that if you look at the morphology of a piece of material that has failed, it's very difficult to assess what was the cause. As I said, there are 5 distinctive characteristics of 5 specific causes of corrosion that you could say, okay, this is due to this or this is due to that. But once again, we have to do detective work. We have to really understand the process to come up with the final conclusion. Well, in this case, the answer to that question below, you see the pits that they have some kind of a U shape or horseshoe shape here. This is a U. You see here, this is a U. This is a U. So the flow direction is in this direction because the U is pointing towards where the flow is going. And that has a specific characteristic and a specific technical explanation why that is. Once again, this is beyond the seminar, but there is a specific hydrodynamics that can tell you why is that U shape is the direction of the flow. And of course, the other thing that you can see here is that the water was basically between, if this is the 6 o'clock position, well, the water was perhaps between the 4 and 7 o'clock position. This is important to know because then if I am going to install a monitoring system, if I install the monitoring system at the 12 o'clock position, definitely I'm not going to be measuring any corrosion. So I need to know the flow characteristics inside my pipeline to be able to locate where my corrosion monitoring device is going to be located. In this case, of course, ideally is to locate it at the 6 o'clock position or from the 12 o'clock position running down a string all the way down to the 6 o'clock position. But the monitoring needs to be located in this region, in the region that I'm showing right now in the screen. Otherwise, I'm going to be saying, well, I have low corrosion rates, and that is not true. So why do we need to know that? Because this is what we want to prevent. Okay, this is no longer a pipeline. This is a clamp line. Look at that. These are temporary forever clamps. Okay, and I say temporary forever clamps because in theory they should be temporary, but then they become forever clamps. And this happened in a specific region of the pipeline where we had a specific flow regime. A flow regime means is how the gas phase and the oil phase and the water phase distributes themselves inside the pipeline. In this specific location, we had a slug flow. And a slug flow is one of the most aggressive flows in terms of corrosion. You would expect to have a lot of corrosion when you have a slug flow because of the high shear forces. Now, what are the influencing factors that drive the corrosion rates, the corrosion rates? Here I have a table showing some of these factors for internal corrosion, okay? Only for internal corrosion. I'm not gonna go through them, but here we have 36 factors. 36 factors, ladies and gentlemen, that will influence internal corrosion rate. And the amazing thing is that all these factors are interconnected. We need to understand each one because each one will affect the other. And then to assess and evaluate internal corrosion, we need to know how all these factors come together, okay? When we look at external corrosion, we have 17 factors. Well, external corrosion, they have less factors than internal, but still it's 17 factors. Altogether, it is 53 factors to mitigate and to maintain the integrity of a pipeline due to internal and external corrosion. Think about it. It's a lot of factors. That is why, ladies and gentlemen, the beauty of corrosion is that everything is interconnected. We need knowledge of every process, every operational variable to assess and evaluate corrosion. I always say, and that's why I've been in this business for 35 years of my life. And the more I learn, the more I know I have to learn even more in this beautiful science of corrosion. I mean, this is one of the science where 2 + 2 may never before. So 2 plus 2, maybe 5 sometimes, maybe 3 sometimes. That's why we need to understand all these variables to understand what's happening with respect to corrosion. And when we're talking about internal corrosion, it's even more. There are many different types of crude oils. There are many different types of waters. There are many different types of flow rates, and they influence internal corrosion. And of course, the monitoring of these variables, they become a key issue, okay? Not only the corrosion monitoring, which is what we are going to be talking about in just 1 second. It is about all these variables that we need to understand, we need to monitor to compensate with the corrosion monitoring to come up with the answer that management wants. Am I going to have a failure or not? That's why I always say, whenever we want to control corrosion, we cannot be wearing blinds. We cannot. We have to have a complete, what I call helicopter view of the system, because there may be some variables upstream that I can control, just twitching something upstream that is going to benefit me downstream. So we need to have a big picture of all our system. So please do not wear blinds. Unfortunately, many corporations out there, they have their chemical treatment people in one area, inspection in another, the corrosion guys in another, the integrity guys in another office, in another division, and the flow assurance guys in another division. Wow, in my experience, all these things are interconnected. You cannot control corrosion without talking to the chemical guy. You cannot control corrosion without having the chemical guy talk to the corrosion, talk to the inspection person, talk to the flow assurance. Flow assurance affects the integrity of the pipeline. So everything needs to be integrated the same way, okay? So now, here we got Mr. Bean wondering, what the heck, how am I going to do to assess internal corrosion? Right? How am I going to implement mitigation techniques? How am I going to evaluate the effectiveness of these mitigation techniques? We can do it, okay? We can do it. And that's the beauty of this beautiful science. First of all, what I always say, we need to learn the principles, the basics of corrosion. You would be amazed how many people at this stage do not understand the very basics of corrosion, the anode, the cathode, the electrolyte, the metallic pad, how that works. If you have a good grasp of that anode, cathode, and electrolyte, there is nothing that can stop you to understand what's going on with corrosion. But you have to know the very basics. And I always say, and this is the propaganda for NACE, that NACE International, of course, they have very many nice courses that can lead you in the direction of understanding the principles of corrosion, whether it is external or internal, etc. Now, one thing that I just mentioned, we need to know the system. Need to know the system. I need to know the patient. Here I am, the medical doctor. I need to know the patient. I need to touch it. It is impossible for me to say that I'm going to control corrosion in a remote way. I have to touch the patient. I need to see where that pipeline is. I need to see where that pipeline is coming from. I mean, it's beautiful that, well, nowadays we are all stuck in our homes and we have to do it remotely. But in my opinion, and that's one of the things that I miss the most, being out there in the field. I tell you the truth, I miss it. I hate it with this virus because I cannot be out there in the field, because we need to know, we need to touch the patient. We need to look at all this data. Nowadays, people don't like to read. They don't like to go through all papers. They don't like to go through the history of the pipeline. And in many cases, unfortunately, that history of the pipeline is lost because maybe the person who knew where the pipeline was going from one location to another retired, and he went in his head with all that knowledge. And if you want to call him now, he probably be in Hawaii enjoying a Mai Tai, and he will not answer the phone, and then the data is lost. Be in the field. You need to have field experience. Here, you may think I'm crazy. That's me basically with an stethoscope listening to the pipeline. What was I listening for? The slugging, the flow, how I was listening the frequency of slugging. Why? Because with that frequency of slugging, I wanted to verify my flow model to see if the flow model was predicting what I was listening into that moment. You are able to listen to that flow. People said that I was crazy, but I didn't care. Okay, so all these once again are interconnected. How do I assess internal corrosion? Well, there are many ways of assessing internal corrosion. One of them is ILI, intelligent pigging. The other is using the NACE ICDA. ICDA stands for Internal Corrosion Direct Assessment Methodologies. Corrosion modeling. Corrosion modeling is always associated with flow modeling. Okay, they go hand by hand. If you ask me, they are a must. Flow modeling and corrosion modeling, they have to be together, especially for pipelines, well, for pipelines, for wells, etc. And of course, corrosion monitoring. So smart pigs, that's inline inspection. That's one way of assessing the integrity of a pipeline. But how do I do in non-piggable pipelines? When there are non-piggable pipelines, I cannot run a pig, so I cannot use my little smart pig that I have right there. So we can use direct assessment techniques. These are the ones I just mentioned. NACE have developed some for external corrosion. They have developed some for stress corrosion cracking, and we have developed a few for internal corrosion. From the internal corrosion, we have the liquid petroleum pipelines, all those pipelines that are carrying liquids, liquid petroleum like oil, products from refineries, etc. We have the dry gas. The dry gas was one of the first ICDA methodologies that was developed by NACE after an incident that happened in the year 2000 in a location called Carlsbad, New Mexico. Then came the liquid petroleum pipelines after an incident that happened in Alaska. And then we developed the wet gas ICDA and what I call the mother of all, the multi-phase flow ICDA. These are methodologies that help to assess the internal corrosion of pipeline, as well that they will help you select where the corrosion monitoring is best to locate them, and they can also give you an action to trigger corrosion monitoring. We talked about corrosion rate modeling. As I already mentioned, from the point of view of internal corrosion, we have 36 factors that influence internal corrosion. Now I want you to think about this. We have 36 factors. How can you expect that we are going to put 36 factors into a mathematical equation to come up with the magic corrosion rate number? Ladies and gentlemen, it's just impossible. It's just impossible to do that. If you look at the wet gas ICDA and the multi-phase flow ICDA, there are many correlations that are mentioned there that can predict corrosion rates. Okay. Now, my recommendation is whatever number you get from those correlations, use them as tendencies. How likely it is that I'm going to have corrosion. But using the absolute number by itself without understanding the process is not my recommendation, because you may be waiting for a nice surprise. So I always said that you need the expert advice or the subject matter expert advice to make better interpretation of the results. Okay, if you look at the list of those correlations, I even have my own correlation. And do I trust that number? Even I know my correlation inside out, and sometimes I don't trust it. I need to know more about the process before I can say, this is it, this is the magic number. You should do it as a tendency anyway. That is my recommendation. I'm going to have fine printing. I said that, but I'm not responsible for it. Once again, when we do internal corrosion rate modeling, since I mentioned we have to do flow modeling also, corrosion rate and flow modeling are key to better and optimize the locations where monitoring can be placed to continuously assess the internal corrosion threat. And then maybe, depending on how well we understand that monitoring, we could use those values to trigger inspections that will then help us assess internal corrosion integrity. From the point of view of now, the other aspect, internal corrosion monitoring. Okay, finally, we are here in monitoring. Now, my experience have shown me that it's impossible to manage corrosion without corrosion monitoring. It is impossible. Monitoring is telling me how bad is the fluid, how bad is my blood in the case of a person, because monitoring, it could be sampling the fluids, sampling the blood, and in the blood analysis, we can get, nowadays, we can get whether we are contaminated with the freaking COVID-19. We can get if we have cholesterol. We can have if we have many other issues, maybe heart issues tendencies. So that's part of monitoring. And monitoring are leading indicators. They give you an alarm before the asset's wall is affected. Before I see something happening to the wall of my asset maybe a tank, a vessel, a pipeline, any asset out there, is telling me, hey, something is going on. Something is going on, okay? Because once again, they evaluate the severity of the fluid, evaluate the severity of the fluid. And one of the most important aspects is they evaluate the effectiveness of our mitigation actions. Without monitoring, it's impossible to determine whether my mitigation action is being effective or not. Think about this. I'm putting a corrosion inhibitor in my line, but I'm going to inspect it, not monitor. I'm just going to go with inspection. How long will I have to wait until I see that that corrosion inhibitor is working? 1 year, 2 years? It's maybe too late because the pipeline is already corroded. I'm not going to say it's too late, but the pipeline is already corroded. I don't want that. I want to prevent that. So the only way that I can manage and I can understand whether my chemical is working is by monitoring. If we don't do this, the chemical companies are going to be very happy. They are going to be the happiest people alive because you have no way of measuring whether that chemical they're putting into your system is working or not. Now, it is conservative. Yes, that's what I want because I want to be preventive. I want to be preventive. So that's why I want to locate my corrosion monitoring system in the worst locations, because what they are seeing doesn't necessarily represent what's happening into the pipeline wall. And then I'm being preventive. And of course, monitoring can trigger inspections. Then they can say, okay, it's time to do an inspection. On the other hand, inspections, Sometimes, and I'm going to talk about them because many companies nowadays, they have permanent inspection tools, and they call it monitoring. Well, there I have a disconnect with that particular nomenclature that they use. In my opinion, they are continuous inspections, not monitoring. Inspections are a lagging indicator. Why? Because when they measure something, even though they may be very accurate, very sensitive, but when they measure something, it's something that is already happening to the pipeline wall. It's already there on the pipeline wall. And that's what I want to prevent. I want them to wait, don't touch my pipe. I want to do everything before it reaches my pipeline. They are very important. I'm not saying they are not. Inspections are extremely important because they will allow us to measure the health of our pipeline. It's like when we go an X-ray ourselves. If we go to the doctor and we go through an X-ray, that's an inspection. And we need to know what is our health. Monitoring, blood sample. Inspection, X-ray or MRI. Okay? So monitoring with an stethoscope, monitoring. Now, they are very important to predict the life, the fitness for service, the remnant life of my asset. Both of them are equally important to assess the health of the asset. Okay? But once again, monitoring is key. In addition to assess the health of the asset, monitoring is key to evaluate the effectiveness of the mitigation technique. I'm going to just talk about a little bit about examples of mitigation techniques. We have here quite a few examples: corrosion inhibitor, scale inhibitor, scavengers, dehydration, process control, cleaning peaks, control of flow velocity, material design, etc. Let's take this, for example. Corrosion inhibitors, scale inhibitors, scavenger, and cleaning peaks. How do I know if they are working? How would I know a corrosion inhibitor is working, or a scale inhibitor, or the scavenger? I need to monitor. How do I know if my cleaning peak is really complying with the cleanliness of the pipe? By monitoring. When we use chemicals, ladies and gentlemen, it is very important to inject them in the middle or in the most important phase inside the pipeline, not directly on the top of the line, because that may cause issues of corrosion. You're going to say, well, corrosion inhibitors can cause corrosion. Yes, they can cause corrosion. So we have to inject them in the center of the pipe so that it mixes properly. And then you need a proper mixing device. In this case, we are showing a quill. I love quills more than spray nozzles because spray nozzles may plug easier than the quills. So here you have a quill, and the quill will generate enough turbulence in this area to enhance the mixing. That is the key for chemical treatment to work. The mixing. The better it's mixed, the better it will work. And in many cases, you may have to inject, in addition of a corrosion inhibitor, a scale inhibitor, etc. So how do I know that it's working? I'm going to give you a true example here. This is pipeline A. Here we have corrosion rates as high as 1.4 millimeters per year. These dark bars are pigging. So I pigged, corrosion rate went down. I pigged, corrosion rate down. Pigging, cleaning peaks, corrosion rate down. No pigging here, corrosion rate back up. Pigging down, pigging down. Another system, pipeline B. Pipeline B, we had no pigging. The dark bar here, pigging, corrosion rate down, pigging, corrosion rate down, pigging, corrosion rate down, pigging, corrosion rate down. How did I know that the pigging was working? By monitoring. By monitoring. In this case, I had such high corrosion rates that I used corrosion coupons. properly located. Okay, so that's another important thing about monitoring. The pigging strategy is working. So monitoring for internal corrosion. One of the things about monitoring, let's talk about first that picture that we see here. If we go to the doctor, we can talk to the doctor and say, okay, like this old guy here, well, not so old, maybe I'm as old as that guy. And he says, well, doctor, you know what? I have a pain right here, or I used to have another pain near my ribs, my throat, is hurting things. Well, I tell you, pipelines, they don't talk. So we are the doctors. We as the corrosion engineers, we are the doctors. But in pipelines, they don't talk. The pipeline is not going to tell you, hey, here I am. The chemical treatment is working fine. Hey, here I am. The pipeline cleanliness is great. Oh, the corrosion rates are controlled. Boy, if you are expecting for the pipelines to speak to you, sitting next to them, you are going to be there for a long haul. You are going to be there for a long time. So you will never hear what they're saying. The only way that the pipeline speaks to you is through monitoring. This is the only way, okay? Pipelines will speak to us through monitoring. And the key of this is to not expect that tomorrow I'm going to put a corrosion coupon or an ER probe or whatever other monitoring of your delight, and you are going to understand that pipeline. When you are learning a new language, it takes a while. It took me about 6 months and a little bit more to learn English. And still, you'd see my accent is not perfect. So to learn that language of the monitoring takes a while. Okay? So don't expect to immediately learn the language. Listen to that. Take one monitoring data, take the other one, look at trends, look at what is the pipeline trying to tell you, look at if things change, look at the process upstream to see if there are things that are changing the corrosive condition of your systems. What is happening? So you have to be thinking that the monitoring is key to get you thinking, to get you going and get you thinking what's going on further upstream, what can I do to mitigate that? A new language, as I said, requires time. So don't get frustrated. It takes time to understand what the corrosion monitoring takes. One of the things that makes it sometimes a little easier is that and this is something that is widely recommended within the NACE community, that you have to at least have 2 different types of corrosion monitoring devices. It will make your life easier, okay? So easier to understand that language. And once again, giving a little propaganda to NACE, because NACE came up with a beautiful article. This is a state-of-the-art document. It's 3T199 2013, and it talks about all the techniques for monitoring corrosion and related parameters in the field application. It's a beautiful document that I do recommend that you get your hands on in it, because it's a beautiful document that talks about corrosion monitoring. Now, arguments against corrosion monitoring. Well, some people say, well, I'm not going to do corrosion monitoring because it is too expensive and it is manpower. How much compared to one corrosion failure? Well, think about that. The line is piggable. I cannot use monitoring. It will interfere with the path of the pig. Well, when this is true when flush mounted type monitoring devices cannot be used, but in reality it's not true, because you can put them in locations that are not in the path of the pigs. The other one, It is an unsafe operation. It's very high risk. Yes, it is. I'm not going to deny that. But so there are many other activities in the oil and gas world are very high risk and even higher risk than pulling out a coupon of a high pressure system. As long as you can carry them safely, they can be done safely. Have you ever said drilling, for instance? Have you ever stopped drilling after so many deaths? Think about it. How many people have died in the drilling? And we never said stop drilling. We are doing it safer. We are having more controls. We are training people more and more. And this is the same thing we can do with the corrosion monitoring in high pressure systems. The other argument, my pipeline carries dry gas or dry crude oil because since it is dry, I don't need corrosion monitoring. False arguments, not true. We said the excuse of dry gas. Well, let's talk a little bit about that. The definition of dry gas with respect to water vapor, we said that, okay, if the amount of water is less than 7 pound mass per million standard cubic feet, or that should have been or, not of, or 112 kilograms per million standard cubic meter, then we said it is dry gas. What is the meaning of dry gas? Here is an example. Here is a typical gas composition. This is the gas phase diagram. This inside here, we have hydrocarbon being condensed. This line, this blue triangle line that I'm signaling right now, is the water dew point. If my pipeline is operating, let's say from this point to this point, when it crosses this line, I'm going to have the very first droplet of water. But I'm going to dehydrate it. So I move this line to this line. Now this is dehydrated line. Now I am operating in this area and I should not have water. And see what I'm saying? I should not have water. Okay? I should not have water because I dehydrated the gas. But I got news for you. Here is a typical incident that happened in the year 2000 in Carlsbad, New Mexico. This was a dry gas pipeline operated by Kinder Morgan, by El Paso company. And here is the failure. This failure, you look at the size of the flame, this failure killed 12 people that were camping nearby. Why? If it is dry gas, we know that if there is no water, no corrosion. But one thing that you have to keep in mind, this is dry gas because we dehydrated the gas in a dehydrating system. What is the reliability of the dehydration system? Is it 100%? Not necessarily. So 1% of unreliability is going to cause water into my pipeline that may get trapped, and then we have corrosion. The other argument, dry crude oil. The definition of dry crude oil is that the crude oil will have less than 0.5% of BS&W. BS&W stands for base sediment and water, mostly water. But then think about it. My pipeline is producing 400,000 barrels of oil a day. That is equivalent to 2,000 barrels of water. Is that dry? Oh, no. Then it comes a very specific property of the crude oil, which is wettability. Which one is wetting the pipeline? Is it the crude oil or is it the water? There is research going on, or there was research going on by PRCI defining what is the wettability and how can we measure that wettability of the crude oil to see which one is going to be affecting corrosion. And thinking of those dry crude oils, here is an example. This happened in 2006 in Alaska. Dry crude oil. And look at this dark thing is not snow. This is not dark snow. That's oil. Okay. And the pipeline failed because of MIC, microbiology influence corrosion. But if there is no water, there should not be MIC. But there is water. because we had little water trapped in the oil. Unsafe operation. One operator, for those that think, well, it is an unsafe operation, one operator in the Middle East have 5,000 corrosion monitoring devices throughout the field. 90% of them are corrosion coupons, which they retrieve 60 to 90 days, every 60 to 90 days. No incidents. I myself used it throughout my career in systems of 1200 and a little bit higher PSI systems in 2,000 different locations, no incidents. On the other hand, one major oil producer suffered one incident when one person unfortunately died. There was a coupon that was on the 6 o'clock position, and unfortunately it died because in the 6 o'clock position, the fitting accumulated debris and the plug got stuck. What was the company resolution? No more monitoring. I want to see how they will manage corrosion. They've been having this for quite a while, and now they are thinking of going back to monitoring because they are realizing that they cannot manage corrosion. Here is the case of, this is the plug, this is what you remove, you take in and out, and this is the fitting. And if you put this, by the way, I just want to make a comment. It is very important to avoid issues also with the fitting, that every time you remove this plug, replace the O-ring and replace the Teflon. Those are the seals. It doesn't cost much to replace them. Replace them because that is the life that is going to avoid leaks outside. That's just a recommendation. So when they are at the 6 o'clock position, you see, they become a dead leg. This is a little dead leg. And this little dead leg can then collect debris. And this debris can make this plug to be stuck and not easy to retrieve. How do I avoid that? If we need to put the corrosion monitoring on the 6 o'clock position, by the fitting with the valve. Open the valve, let it drain the debris, or push the fluid into the system. Or locate it at the 12 o'clock position and run it all the way down. Once again, training, very important. You have to train the people, because training will prevent any issue. Use people that are trained. I recall that picture that you see there is because I train all the people that use my high pressure systems to avoid these issues. Or you can buy tools. These are specific tools that have a similar deal with this valve, but they have it on the tool that you can open the valve and drain the water in. This is a system that is sold by Cosasco, for example. Or if you want to avoid any risk, outsource the system. Have Cosasco or somebody expert to take it out. Okay. Well, Cosasco, I've been giving propaganda to NACE, so now it's the propaganda to Cosasco. So you cannot outsource the system to experts. They'll do it. I mean, as a matter of fact, this another field that I worked in the Middle East, it was outsourced. The system was totally outsourced by trained people. Corrosion fittings can also corrode, so please do not lose sight of this. Okay, here we have the fitting. You see now, because of corrosion, we lost the seal here. So it's only the O-ring maintaining the seal. We may have leaks. See, we may have leaks. Okay, how can we avoid this? We can prevent using cladded fitting with corrosion-resistant alloys. This is an example. Here is the fitting, and here you see the cladding. This is cladded, so that if we have a corrosion-resistant alloy. Remember, the use of a corrosion-resistant alloy, that doesn't mean that it's immune to corrosion. It's immune to that specific condition. If conditions change, you may have to change the corrosion-resistant alloy. Now, if you have this issue in your system, the other thing that you can do, if locating the fitting at the 12 o'clock position, extending the coupon to the bottom, because now it's not exposed to the fluid, directly to the fluid. You're not going to have debris sitting in there or bacteria sitting in there. If you already have one place, one of these fittings located at the 6 o'clock position, to prevent leakage, you can use high pressure caps and basically condemn them, don't use it, and replace it in the next shutdown. But the use of high pressure caps is important, whether it is in the 12 o'clock position or in the 6 o'clock position, because the high pressure caps will prevent a leak. Okay? It will condemn the use of your corrosion monitoring device in that location, but it will prevent that leak through the plug. So high pressure caps, I use them all the time, for example. Now, piggable line excuse. We can, once again, we can always put it on the bottom of the line or put it away from the pig. This is the pig. The pig debris comes in. It's going to go this way, most of that pig debris. Only a little bit is going to be trapped right here on the pig trap. But as the fluid is going, you can install them here. You can have as many as you like. You can have your weight loss, ear probes, and sampling. Sampling is very important to have. Because why is it important? Because one of this is besides the point of monitoring, but this amount of peak will never reach here. And then we say, well, we only had a little bit of debris. Yeah, because most of the debris went on this bypass. So if we start taking samples from the very beginning, taking samples, we can guesstimate how long this peak debris or the amount of peak debris that we have in the pipeline. Okay. Now, corrosion monitoring reliability. The reliability of the data increases by using 2 or more distinct monitoring devices, at least 2. Ladies and gentlemen, location, location, location. This is key to assess the pipeline condition. We want to have it where the water is. We want to have it in the worst location to be more conservative. Okay? Once again, if we are monitoring corrosion, and this is let's say this is a wet gas line, and my monitoring is here, unless we are monitoring for top of the line corrosion, well, we are not doing anything. If this is oil, if this is oil, the water is going to go here. So here then we pull it out. I say, hey, there is no corrosion. Of course, you can show this to the regulators. I say, hey, regulator, I don't have any corrosion. Look at the coupon. Well, but is the coupon installed properly? That's what we need to. That's what we need to know. We can do this. I love this configuration. To tell you the truth, I love this configuration. Why? Because it gives you a very nice profile of your system. Now you're going to say, well, but it's going to interfere with the pigs. Well, put it in here, put it in here, put it in here. Or to make it a little bit more challenging, whenever you run a pig, take it out, which I don't recommend because you may forget, and then there goes your monitoring, or your line is no longer piggable. Or you can put them on the bottom of the line, as I mentioned. Once again, flow modeling is key to determine where water will accumulate, and then we can install our systems in the worst locations. How about accessibility? They say, well, you know, the thing is that I have this pipeline, and where corrosion is worse is in this low spot of the pipeline, but it's in an area that is inaccessible. Really? What is the meaning of inaccessible? Well, it is underneath a building. Okay, that I can understand. If the lowest part of a pipeline is underneath a building or underneath my house or your house, you don't want your COSASCO guys coming into your house to retrieve a coupon, right? So you have to do with what you can. Normally, what happens is that accessibility is driven by where it's easier to pull the coupons, which may be on the stations upstream and downstream. But there is no reason why you couldn't do it in the middle of the pipeline. When you can do that in the middle of the pipeline, it's a matter of money. It's a matter of willing to do it right. This is an example. This example is for a 36-inch pipeline that goes from Macaé. Macaé, I mean, one of the producing fields in Brazil is Campos Basin. Campos Basin is about 100 kilometers offshore from an area called Macaé. Macaé is a city. All the production comes to Macaé, and from Macaé goes to Rio de Janeiro to the refineries. So this pipeline is a 36-inch pipeline carrying the production from Campos Basin, from Macaé to the refinery. And this, as you can see the field, this is the middle of nowhere, but they found that this was a low spot where they would have a lot of corrosion. How did they determine this low spot? Because of flow modeling. And in the middle of nowhere, they built this bunker. Look, they built this bunker. And inside this bunker, this is the pipeline. And these are different type of corrosion monitoring devices. This is one, and we are gonna see a couple more. This is other corrosion monitoring devices. And here we have corrosion monitoring devices in the middle of nowhere. Can that be done? Yes, it's gonna cost a lot more money. Yes, it will cost more money, but you are being preventive. What would be the cost if that pipeline that carries the whole production of that field to Rio de Janeiro fails? You're going to have to shut down production. 2 days of production pays for this bunker. Type of corrosion monitoring. I'm going to give you a little bit of what I think the trending of monitoring was. Okay. First of all, coupons. Coupons are the oldest type of corrosion monitoring that there is out there. I tell you one thing, ladies and gentlemen, I love the coupons. I love them. I have a colleague that doesn't like them very much, but I do love them. They provide you with physical evidence. You can measure pitting. You can look at the sludge that accumulates on the coupons that may be due to bacteria. So they could also be a way of monitoring bacteria. Then we came up with the ER probes, corrosion to measure erosion. The FSM is a field signature method, which is basically what you saw right here. Right here, this is the FSM. The FSM works basically under the same philosophy of an ER probe, but the disadvantage is that your pipeline is the probe. So I don't like them. I don't like them. We have galvanic probes. We have linear polarization, which are basically electrochemical techniques. They've been used for a while. The electrochemical techniques, they work well in clean environments, especially LPR, polarization, and other techniques like electrochemical noise and AC impedance. In my experience in the field, they are too complicated to be used in the field. You really need to, I mean, they are good for a lab, and even in the lab, you may have a lot of issues with them. So I don't know. I have no experience because I've never used them in the field. In the labs, I know people that have used them in the lab and they are not happy either because of the issues. LPR and polarization, you need clean fluids. That means you cannot use them in oil system. And if you're using them in water, well, it's gotta be relatively clean water. You have high-speed ER, which is basically an advance from your old ER probes. Okay, in this case, we're talking about the microcore, that is a specific trademark for COSASCO. And one of the things that we've done today is data transmission. Unfortunately, and this would be a message for my COSASCO hosts, why haven't we come up with better instrumentation to measure corrosion? I'm not talking about data transmission. I'm talking about corrosion monitoring devices. We are using technology that is 30, 40 years old. Yes, we have improved the noise by example of the microcore. We improved the noise level, et cetera, but the technology we are using 30-year-old technology. We need better technology. I hope my COSASCO hosts don't get mad at me by saying this, but it's important because as users, we need, I mean, we've gone to the moon just or to the space station just a while ago, in back and forth with the astronauts now wearing fashionable astronaut suits and all that, and we cannot even come up with a better instrument. We need better instrumentation. So, well, back to the data transmission. This is where we had a lot of improvement, because you can now have all your data transmission to your SCADA system, which would be beautiful because you can correlate your corrosion rates with your operating characteristics, your operating conditions, and then you can deduct more what's going on into your system. You can transfer that to your computer or to yourself. You corrosion engineers out there, don't ever let them send those data to yourselves, because then you will never sleep, or you will be sleeping and on the phone is going to go beep, beep, corrosion rate high, beep, beep, corrosion rate high. You don't want that. All right. So corrosion coupons, as I said, I love them. They are excellent. If you know how to interpret the data they give you, how to analyze them, they give you beautiful data. Remember, it is a new language, requires many trials. It is an intrusive system. We can do extended analysis. Extended analysis means microscopic analysis or analysis using a specific equipment, sort of like Kion said, that give you the profile and the 3D beautiful stuff. So, and then can give you pit initiation. One operator in Alaska uses pit initiation to determine whether they have bacteria activity or not. How can they say that? Because they have had the experience, they understand the coupons language, and then when they see pitting, they say, okay, I'm having issues with bacteria. So it's all about trending. This is an example where we pull out a coupon with some stuff on it. This stuff, immediately we can do bacteria, and this would be sessile bacteria. Ear probes, once again, the understanding what the pipeline is trying to say, these probes may take time and experience, but once we get the language, they are very useful. The learning curve may be reduced by using a secondary monitoring device, high resolution ear probes, and they give you corrosion rates in real time. They are good for chemical optimization, because you can be optimizing your chemical in a matter of a few days, of a few weeks, instead of a coupon that may take you 1 or 2 months to optimize your chemical. It is an intrusive system unless you put a flush one. Well, the coupons can also be flush mounted. Okay? They can be used in any environment. So will the coupons. The coupons can also be used in any environment. Data can be transmitted to the SCADA systems, and we can correlate it to the operational variables, as we mentioned before. We can also use them to estimate erosion rate. One of the drawbacks is that if you use them in H2S environment, they can be affected by iron sulfide, because iron sulfide is conductive, and then you may think that the corrosion rates are dropping, and that may not be true. So that means that maybe when that happens, you're going to have to retrieve the probe, clean it, put it back in system until they come up with a self-cleaning ER probe. I'm waiting for that, a self-cleaning ER probe. They do not measure pitting rates. LPRs, well, as we mentioned, they are electrochemical means. They do corrosion rates also in real time. They are good for chemical optimization. It is an intrusive system. Data can be transmitted likewise in SCADA. They can only be used in clean electrolytes. Water has to be clean, and if we have oil, it's got to be very low oil-water ratios. Can be affected also by FEF or by iron sulfide. Do not measure pitting rates. UT probes. You heard me say before about about inspection and probes. In my opinion, UT probes are an inspection tool. No matter how sensitive they are a continuous inspection tool. They will measure something once your pipeline wall has seen it. Is it too late? No, it may not be too late. Okay, but since they are not measuring the fluid characteristics, then you gotta position them in the right location where corrosion is being highest. And even then, corrosion may be happening just next to the probe and you are not seeing it. They use a pulse echo method to directly measure the wall thickness in the location where the probe is placed, only in the location where the probe is seeing the pipeline wall. The language is easier to understand because it immediately gives you a wall loss. This is one advantage. You don't have to go through a learning process because they measure already wall loss. Wall loss are in real time. These may be good for systems with very high corrosion or erosion rates. Okay? You will place them where you have the highest corrosion and or erosion rates. Once again, but they are lagging indicators. It's already the pipeline wall that the one that is suffering. It is non-intrusive because you put it from the outside of the pipe to measure what's going on inside. So you can put them in any environment. Data, once again, can be transmitted to SCADA systems, cell phones, anywhere. Useless for chemical optimization. Hey, forget it. They cannot be used for chemical optimization because the response time is going to be too long. Before the pipeline wall sees something, it may take 1 or 2 years, even in the high corrosion and erosion rate view. This monitoring device is a lagging indicator. It measures corrosion when the pipeline has suffered damage. It is a continuous inspection probe. This is what I just mentioned. Despite the claim high sensitivity, they will only measure wall loss where the probe is placed. It can miss corrosion locations. You can use many probes at one location to increase the reliability, but then you gotta be thinking about dollars. And here is an example in which you have many of these right here in a bend. Well, because in a bend you will expect to have perhaps more erosion obviously because of the hydrodynamics, and then you can have that. But it will measure right here, but in between, what happened in between? You are not measuring something that is happening in between. So there are many other monitoring devices out there, many others that we have not talked about. Tips for a successful monitoring and thus mitigation of corrosion are: select the monitoring type most suitable for the fluid conditions, for your fluid condition. Don't expect that every monitoring is good for everything. It's gotta be specific to your fluid condition. Location, location, location. Please put it where corrosion is worse. You wanna be preventive. And for this, you may need flow modeling. Select at least 2 types of monitoring devices. Be patient while learning their language. Don't despair. Look at the trends. And when you look at the fluid analysis, that's another type of monitoring, fluid analysis. Do the correct fluid analysis, the correct blood pressure, and blood sample. And once again, where am I doing that fluid analysis? There are many species in the fluid that require that they be done on site. Okay, but it doesn't make sense to send them to the lab because you are going to lose a lot of information. So you have to do many of those on site. For example, pH, alkalinity, bacteria, depending on the type of bacteria that you are doing, you are going to have to do it on site. Okay, So CO2, dissolved CO2, dissolved H2S, many of these need to be done on site. Make sure that you follow the proper procedures to do the fluid analysis, because you may be losing a lot of important information if that is not done correctly. Select a monitoring supplier with track record. Hey, well, this I'm from, okay, here I'm gonna buy Carlos Palacios' monitoring tool. Where is he manufactured? Well, I have a nice garage, and in my garage I have this. No, look for people with track record. Okay. First of all, I do not fabricate monitoring devices. So make sure your monitoring supplier provides you with the technical support until you have learned the language and beyond. There are many of these suppliers that they are happy to sell you the tool and then they will forget about you. You do not want that. You need a supplier that runs with you all the way, that give you the technical service you deserve. Okay? You can always outsource the service of monitoring to an experienced company with track record and expert personnel. Corrosion monitoring and integrity assessment. One approach that I use to increase the integrity assessment when using corrosion monitoring. Here is what I do. I use my models, which is this term right here. This is my modeling part. This includes, once again, corrosion and flow modeling, monitoring, and inspection. These alpha, beta, and phi are weighting factors. So from the monitoring, from the flow modeling, with my monitoring and inspections, all of them combined together will increase the reliability of your system. You will learn the language more clearly, not with the Spanish accent that I have right now. So you will have a very nice, soft, smooth language when you combine all these techniques. And basically, as I mentioned, all these alpha, epsilon, delta, alpha, beta, and gamma are basically weighting factors. And the trick is defining them. And the way you define them is by listening and the experience that you get from your monitoring and inspection and the modeling. Okay. If you are using a reliable inspection technique such as an ILI, of course, the weight of an ILI is going to be higher than any other of the other ones. In my book, I said alpha is never zero because alpha will compensate with the errors of any of the techniques that you see out there. So make sure that monitoring systems, whatever system you choose, are included as an integral part of your asset integrity management program. Okay, it's important. Integrity management, everybody integrated. When we do no monitoring, no corrosion management. This is one of the key takeaways that I want you to take from this seminar. Once again, I do not sell any monitoring device. I do not work for COSASCO. I don't pay royalties for saying this from any of the companies, but it is my experience. No monitoring, no corrosion management. Okay, I am an independent consultant and I don't receive any royalty from anybody because I maintain my independence the way I have for many years. So, but my experience is no monitoring, no corrosion management. Just a basis for any management system. Any management system is composed of these 4 or 5 elements: plan, do, check, act, and a continual improvement. And this, of course, when we're talking about corrosion management, this can be the topic of another seminar. It's a beautiful area, an interesting area that we can talk in another seminar. Corrosion and integrity management, I have said it all along. It is an it's a team effort. After all, we are on the same boat. We are on the same boat. It's not like, well, I'm sure glad I'm on at your end. Well, the boat is gonna go drowning all of them together. So finally reaching the end, once again, write your questions in the chat of the application located at the bottom of your screen. I'm gonna stick around for a little longer until the host tell me to shut up. So, and we thank you so much for your time. Any issues or any activity you want with COSASCO, you can contact David Velasco, even though I apologize, David, I don't know why they became blue, your email, even my email became bluish that you can not barely see it, but it says dvelasco@cosasco.com. My name, once again, Carlos Palacios. My email is cpalacios59@gmail.com or cmatq@gmail.com. So thank you very much for your attention. I hope everybody's still around and you haven't fallen to sleep. And I turn it back to you, David.
Thank you very much, Carlos. Yeah, your slide is it's okay. We can see the emails. So
Okay.
basically, I want to thank everyone here, and I already opened the chat for everyone to see, and everyone can send the proper questions if you may have on these sessions. I would like to thank Carlos Palacios for all his help, and also to CMATQ LLC for being our partner on this webinar. So in the meantime, you write down the questions. I would like to invite you to follow up COSASCO on our LinkedIn profile and also on the webpage, when you are going to see every single release of new technology, that as we are always developing better equipments, so you will see that information over there. So please link with us through LinkedIn and also follow us on our webpage. Also on our social media, we're going to post the next webinars and activities to increase your knowledge on corrosion and relatives. So please stay tuned on each one of our social media to follow up on that. So once again, please raise your hand or send your questions to the box, and I will see if there's any other questions. Carlos, what are the NACE standards for internal corrosion assessment? They might be mentioned in the email that will be sent later. That's one of the questions.
Well, if we're talking about the internal corrosion direct assessment, all of them are in the presentation. They are for liquid petroleum is SP 0208 2008. For the dry gas is SP 0206 2016. For the wet gas is 0110 SP 0110 2018, and for the multi-phase is SP 0116-2016.
Okay, great. So now we do have a lot of messages saying thank you, excellent presentation, great presentation, congratulations. But apparently there is no more questions beyond that one from NACE. One extra question is, to control corrosion, it is not necessary to control the MIC.
Yeah, of course, it is necessary. MIC is one of the main issues. Oh well, yeah, well, I didn't put it in the mitigation techniques. I should have put biocides, but yeah, well, yeah, I should have put biocides there. But definitely, MIC is huge.
Okay, great. In case that picking inspection is not possible, what other strategy to get an integrity assessment?
We use the NACE ICDA methodologies, or any if it is for internal corrosion, we use any of the ICDA methodologies, or for external corrosion, we use the external corrosion methodologies. And NACE has a course called Direct Assessment, and that teaches you how to use all those standards. But if you are a NACE member, you can download the standards, and then you can use them to assess your specific need.
Okay, how to monitor CO2 partial pressure, which accelerate corrosion in the line. At one monitoring position, we shall will put our coupon of proofs.
Okay, when we're talking about CO2 corrosion, basically what we monitor is the gas quality, no? So we monitor the amount of CO2 that is in the gas or whatever is dissolved in the water. And to do that, you have to pull a sample. I mean, you can take a sample from the gas and then do either chromatography or use dragger systems to measure the amount of CO2 that is in the gas. And then depending on the pressure, you can calculate your partial pressure. Or if you want to calculate how much CO2 is dissolved in the water, when you have to take out a water sample and do the dissolved CO2 analysis right there on site.
Okay, the last one will be from your experience, what is the best corrosion prediction model you recommend?
No, I would say mine, of course. No, I don't do that. I have my own, which I use. As I said, I use it with my experience for the 35 years of exposure in the field. But I mean, I don't like to recommend any because they all have a specific good things and not too many good things. So that's a question that I rather don't answer. You know, of course, if I am being selfish, I would tell you mine once again, but I rather you take a peek and see what best works for you.
Okay, that's great. There are some extra questions coming up. I will forward this to you, Carlos, at the end of the presentation of the webinar, and we may be able to answer them later. So far, I would really like to thank you, Carlos, for all your help on this webinar, and hopefully we can have you here very often in future webinars. And for all the attendees, thanks again for having this time for us. And I hope this webinar is helpful for everyone. So thank you once again.